In this video, we're going to continue working on polynomial and rational inequalities. Let's look at the next example. We have x minus 1 times x plus 2 times x minus 4 is greater than or equal to 0. In this case, we're looking for where the polynomial is above the x-axis or equal to the x-axis. That means greater than or equal to 0. Above or equal to 0. So we're going to find outputs that would be above or equal to the x-axis. I can do this by identifying the zeros of the polynomial. I have solutions or zeros that are equal to 1, -2, and 4. I will label those on my interval number line that's given. Identify where positive and negative infinity tend toward. Label my critical values, -2, 1, and 4. From here, I'm going to just do a very quick sketch of a polynomial of degree 3 with 3 different or unique roots or zeros. I know that it's going to look something like this. And I don't even need my vertical axis. I just know that it's going to tend toward negative values as outputs as x approaches negative infinity. And it will tend toward positive outputs as x approaches positive infinity. So when I know that, I can anticipate where my function will be above or below the x-axis. I can see that it will be negative or below the x-axis to the left of -2. It will be above the x-axis on the interval from -2 to 1. Below the x-axis on the interval from 1 to 4, and above the x-axis from 4 to infinity. Again, a quick sketch of this will look something like this. This being said, I need to find where my polynomial will be greater than or equal to 0. I'll highlight it with a green highlighter. This is wherever the function is above the x-axis. This will occur on the interval from -2 to 1 and on the interval from 4 to infinity. Writing the interval for which this happens, I have to double check what my inequality says. Notice that my inequality says greater than or equal to 0. Since that's the case, I have to include the endpoints because the endpoints are where my inequality equals 0. My inequality or interval for which the solution exists is open bracket -2 to 1 close bracket union because I'm uniting 2 separate intervals, open bracket 4, comma infinity, close parenthesis. And the parenthesis is because of the infinity symbol. In this case, we have 4.32 x squared minus 3.54x minus 5.34 is less than or equal to 0. It's not obvious how this will factor. I think I will use my graphing calculator and see if I can find some obvious intersections with the x-axis. Y equals 4.32 x squared minus 3.54x minus 5.34. I'll graph that. And I'm going to look at the table of values to see if there's any obvious intersections. That would be where y equals 0. So it's somewhere between -1 and 0 because the signs change from positive to negative. But it's not at an integer value, so that means that, and you can see it, there's also an intersection with the x-axis between 1 and 2. So I'm going to have to use the quadratic formula. But I can see that on the interval from -infinity up to somewhere between -1 and 0, I'll have an intersection where the function goes from positive to negative. So to just really quickly sketch this, the function is going to look something like this. And now let's find those values of x for which the function changes from positive to negative values. X is equal to -b plus or minus the square root of b squared minus 4 times 4.32 times -5.34. And this again seems like a good place for a calculator. All over 2 times 4.32. Since I have a negative here on the second part of the discriminant, I'm just going to recognize that that will become a positive and then just multiply 4 times 4.32 times 5.34. And then I'm going to take the square root of that to get 10.2375. We'll just say 10.24. All over 2 times 4.32. So let's just make that 8.64. So we have two solutions. X equals the positive version, so 3.54 plus, let's just arrow up and add that, equals 13.77751, etc., divided by 8.64. So we have 1.59. Now let's do the negative version. And then divide it by 8.64. And we get negative 0.775. So -6. So 1.59 and negative 0.775. So we'll just round it up to 7/8. Now that we've done that, we can write our solution because we know where the function is less than or equal to 0. The solution is less than or equal to 0 on the interval from -0.78, including it. So open bracket -0.78 to 1.59, close bracket. Now let's take a look at exercise 2, where we need to solve each rational inequality. In this situation, we have a rational inequality where the denominator would be a vertical asymptote. So our vertical asymptote will be at -1. So you cannot include the endpoint no matter what, because it's a vertical asymptote. And the 0 of the polynomial will be at 5. So we have a vertical asymptote at x equals -1, but that means you cannot include that value. So just be very careful. Now remember, since the rules for multiplying sign numbers are the same rules for dividing sign numbers, we can use the factors as factors in a polynomial just to check where the rational function will be positive and negative. This is a parabola if it wasn't divided, opening upwards, and so my function will be positive, negative, and then positive again. Now remember, this is a rational function. It's going to be positive and negative in the same places that a quadratic would be, but in this case you have to keep track of the vertical asymptotes and what that does to the factors. So our rational function will be positive on the interval from -infinity to -1, not including -1, and from 5 to infinity. It will be negative on the interval from -1 to 5. Since this is less than and not less than or equal to, we can say that our interval for which the rational function is less than 0 is from -1 to 5.